So, after discussing scattering problems and solving them, we're now going to talk about bound states. I'm going to introduce what a bound state is, how it is different, or how it's the opposite of scattering. So I'll introduce the theory and how we think about these problems. And then we'll go on to solve an example. The half infinite well, this one here. And then we'll solve a second example, which doesn't have as much to do with bound states. Well, it is a bound state, but it's sort of finite. Well, it's an infinite well with a delta inside. We'll be able to make use of the parity theorem that you proved in class. I'll state it again and use it to solve the problem. So this is our plan for today. So let's start by explaining the difference between scattering and bound states. I'm going to explain the difference with an example. I'm going to consider finite well given by this potential. This is a finite well. The potential is 0 outside the well, and it is minus V0 in a certain area between 0 and L. Now, there's a physical condition on the energy. The energy must be larger than minus V0. Energy cannot be below the bottom of the well, but it can be either negative or positive. So E can be either here or it can be below 0, like this. Now, last week we spoke about scattering. And this was for the case in purple where E is larger than V0. When E is larger than V0, the particle can extend to minus infinity, can extend to plus infinity. The problem is non-normalizable. We spoke about this. Because the particle can extend everywhere, we have to deal this with as a scattering problem. You've actually solved this exact problem in your homework, if you remember. If you don't, then solve it again. The energy here, in the scattering problem, the energy is given as an initial condition. We were not asked to find the energy, but we were asked to find, the task was to find R and T, the reflection and transmission coefficients, as a function of the energy. And then we saw different limits. When E goes to infinity, T goes to 1, so different limits. But the energy was never something we were looking for. It was always a given initial condition. According to the energy, we know the momentum of the particle coming in, being scattered. And we always try to find the coefficients. A good way to think about it is think about the classical picture. Always helps. The classical picture of course tells us that the particle can be anywhere. Of course, if the classical particle is here or here, its kinetic energy changes because the potential changes, right? So if it loses potential energy, it'll gain kinetic energy. So a classical particle will be faster here than it will be here, right? But it can be anywhere, and that's why this is what we call a scattering problem. If the classical particle could be anywhere, then we're dealing with a scattering problem. How do we solve this problem? We split up space, we write down a wave function, and use boundary conditions. You've done this. I don't have to go over it again. What we're going to talk about today are bound states. And bound states, so what we get in the blue case here, when E is below 0, E is negative. In this case, the particle will be inside the potential well. And because it's inside a potential well, we expect discrete energy levels. In this case, the energy was continuous, was a given number, not a number, it has units, but a given energy which is a continuous spectrum. In this case, we're expecting a discrete energy spectrum, and indeed we will find that very soon. If you think about the classical picture, then the particle can only be inside the well. The particle in the blue case, for E smaller than 0, the particle cannot be here. It cannot exist here. It doesn't have enough energy. It can only exist inside the well. Now in quantum mechanics, and this is what we call it bound. It can only be between 0 and L. This is why it's called a bound state. Because it is bound to a certain region in space. That's where it comes from. In quantum mechanics, the particle will still be more or less confined to the region between 0 and L. But this will probably obviously will not surprise you, but there is a certain probability to be inside the classically forbidden region. So there is a finite probability to be either in x larger than L or x smaller than 0. This probability can also be found. Okay, so this is the big difference between a scattering problem and a bound state. They are the opposite. In principle, different.
Can I ask a question?
Sure.
When we say that the particle can be in the forbidden area, does it mean that after a certain amount of time he will be able to move out entirely, or that for all time he is confined to more or less the boundaries of the potential well?
So what we're going to do is we're going to find eigenstates of this function. Eigenstates are stationary, so time isn't really relevant. You're asking that if I, as an initial condition, put a particle inside the well, will it, in a couple of days, still be inside the well, or will it go out?
What I mean to ask is that if we, for instance, take two particles, both of them we can find outside the well, but...
Outside the well?
Yeah, outside the well.
So they're scattering?
No, because it's one of them can be outside the well, but in the more or less forbidden area.
But if its energy is larger than 0, who cares? There's no forbidden area.
So what will differ between them is only the energy,
Yeah.
even though we can find them both outside the well.
If E is larger than 0, there is no classically forbidden area. Because the classical particle with E larger than 0 can exist here. Only if the energy is smaller than the potential, it cannot exist.
It can, to a certain limit.
Classically.
No, I'm talking about the quantum mechanics.
So quantum mechanically, we will see. It's going to be an exponential function in here. We'll see it. I don't understand your question.
I got my answer.
Okay. I'm happy. More questions? Okay. So, classical picture, quantum mechanical picture, and the task, of course, will be to find the energy levels. And we can also find Eigen Functions of the well. In order to do it, we need to solve a very familiar eigenvalue equation. We call this the time-independent Schrodinger Equation. I hope you've heard of it. I've heard this equation before. So we'll write down the equation. It'll prove very useful to write the energy as minus the absolute value of the energy. Because we are talking about cases where the energy is strictly smaller than 0, it is much easier to write it down like this, minus the absolute value of E. That way we don't have to be confused. That way we won't get confused. We don't have to keep track of E being a negative number. So the Schrodinger equation of this problem is minus h plus squared over 2m ddx squared plus v of x This is the well-known Schrodinger equation. The only difference to what you used to see is this absolute value here in the minus sign. But that's just the energy. Now, as in the scattering case, you have to split up space. So we call this region 1, this region 2, this region 3. And we then solve the Schrodinger equation in each of the regions. Inside the potential well, where E, sorry, that's Q here. Inside the potential well, where E is larger than the potential, we get oscillations. And outside the potential well, in region 1 and region 3, we get exponentials. And usually we'd have here also the second exponential, but I already eliminated it due to boundary conditions because I need it to be finite. I need this to be finite at minus infinity, and I need this to be finite at plus infinity. So I already eliminated the other exponential. By the way, I'll just write down k and q. K is the root of 2me divided by h bar, and q obviously v naught minus e, the absolute value, is larger than 0, which means that q will be a real number. I went a little quick here, but I'm not going to solve this problem to the end. I think you already solved this problem in class. We're going to solve the half-infinite potential well. I'll go over this step a little more carefully when we actually solve the example. But just want to state the algorithm, how we solve the problem. So we have the Schrodinger equation, we find the wave function, and then the third step is to use boundary conditions to find the energies. So we get an equation with the energy. Now, what will happen in most cases is that we will not get an analytical expression for the energies. In most cases, we will get a transcendental equation for the energies, and that can be solved graphically, which is what we will do. Does everybody know what a transcendental equation is? The transcendental equation is an equation that cannot be solved implicitly. So for example, take the function, say, e to the minus x equals x. And solve for x. So you can take the logarithm on both sides, but then you'll end up with minus x equals logarithm of x, and you still can't solve it, right? So you cannot find it, and you cannot eliminate x on one side. It's not possible. That's what's called a transcendental equation. And the way that you solve these kinds of equations is by plotting them. So you make a graph. Here's x, the x-axis. You then plot the left-hand side and the right-hand side. So this is x, the right-hand side. Then you plug e to the minus x. Sorry. Yeah, it goes to 0, right? Right, so you plot this, use a computer to do so, and then this equation is satisfied when these two functions intersect. So here. So I have to plot this on a computer. You then zoom in, read off the value here, and you can read off the value of x that satisfies this equation. That's what's called a transcendental equation, and that's how we solve it. Okay, so I've talked a lot. It's about time we do some actual problem solving. The algorithm is quite simple. Set up Schrodinger's equation, find the wave function, and impose boundary conditions. It's the usual procedure. And we'll make an explicit example, so you'll see exactly how it works, and we'll be able to deal with the subtleties that we meet on the way. Any questions about how to solve problems? Good, let's do so. Exercise half infinite potential well. So we're looking at potential v of x that is infinite at a smaller than 0, that is equal to 0 within some region of length L, and that is then equal to v0 outside that region. So make a plot of this well. That's not what I wanted, sorry. This is the x-axis. This value here is v0. Okay, so this is what we're looking at. And the task is to find the eigenenergies and then we want to find minimal v naught for at least one bound state to exist. And then we want to find the Eigen Functions, I think. Yep, I want to find the Eigen Functions. This is the task. Okay, is the problem clear? So the first thing we have to determine is the relevant energy interval that we have to consider. Not all the energies have to be considered. In order to determine the relevant energy interval, always think classically. So obviously the energy must be larger than the bottom of the well. So we must have E larger than 0. On the other hand, if E is larger than V0, then this particle will be not entirely free because it's infinite here, but it will be free on this side. It'll go to plus infinity. So it won't be normalizable. So in order to be in an actual bound state between 0 and L, we also need the energy to be smaller than V0. So these are the only energies we have to consider. Next, we split up space. And solve the Schrodinger equation. The regions are obvious. There's the region exactly the same like the potential. So there's the region where x is smaller than 0. There's the region here inside the well, and the region where the potential is higher than the energy.
Can you please explain again why the energy must be smaller than V0? Like, why can the particle just...
No, it can be larger than V0 physically, but it won't be a bound state. We're looking for bound states. Find the eigenenergies of the bound states. So we said that. We're looking explicitly for bound states. Of course, the problem can be solved for E larger than V0, but then it's a scattering problem, which is not what we're trying to do right now. Okay, so the easiest region is region 1. What is the wave function in that region?
0.
It's 0, obviously, because it's infinite. The potential is infinite, and the wave function is 0. We spoke about this a couple of weeks ago. So that's easy. In the other two regions, we have to set up the Schrodinger equation. So the Schrodinger equation is minus h bar squared over 2m. In region 2, because the potential there is 0, which is just a kinetic term, and when x is larger than L, we also have the potential term so with the kinetic term and the potential term for psi 3. As usual, we multiply the entire function by 2 over h bar squared. We move v0 to the right, and then start replacing all of the constants by k's and q's. And when you do this, you have to watch out to do this properly, because you don't want k's and q's that are imaginary. You want to keep your k's and q's real numbers, which means your k squares and q squares have to be positive numbers. So we get psi 2 double prime of x equals minus 2me over h bar squared psi of x, and we get psi 3 of x prime equals minus 2m e minus v0 over h bar squared. Psi 3 of x. So in the upper equation for psi 2, the replacement is simple. This thing is a positive number, so this is k squared. In the second case, e minus v0 is negative, because we're looking at cases where e is smaller than v0. That's why it's important to think about this before you start. If e is smaller than v0, then e minus v0 is negative, but the minus sign beforehand makes it positive. So we replace this entire thing, including the minus sign, by q squared. Q squared is then a positive number. It's very important not to get confused here. So we end up with two equations. Psi 2 of x equals minus k squared psi 2 of x, and psi 3 double prime equals q squared, no minus, and psi 3 of x. These equations can be solved immediately. These are auxiliary, these are exponentials. So we find psi of x equals 0 for x smaller than L, for x smaller than 0, A e to the ikx plus b e to the minus ikx inside the well, and e to the qx and e to the minus qx at x larger than L. Everything clear so far? Okay. Now we use boundary conditions. Right? We have a couple of unknowns. After you solve a differential equation, you're always left with unknowns. The next step is always to impose either boundary conditions or initial conditions. It's a spatial problem, so we have boundary conditions. How many boundary conditions do we need? So it depends how many unknowns we have. How many unknowns are there?
No, we don't know the energy.
There are 5 unknowns. We have 4 integration constants. A, B, C, and D. And the energy. The energy is unknown. Remember, we're trying to find the eigenenergies. So there are 5 unknowns, which means there's 5 equations. Right? The first one's obvious. Normalization. And then we have another 4 boundary conditions. Okay? So don't be confused. There are 5 unknowns, because the energy is also unknown. But you still only need 4 boundary conditions, because you always have normalization. You get them for free.
But are we interested in A at all? Because usually, like when we solved using R and T,
It was normalizable. Scattering problems, they are normalizable, so you cannot use the condition and you're left with the constant in the end. But in this case, you're in a bound state that is normalizable, so all of these constants can be determined. The only reason not to do it is laziness, and that's not a good reason.
Doesn't C immediately equal 0, meaning that we don't actually need an extra equation?
Yeah, it equals 0 because of boundary condition. We'll do it in a second. But yes, obviously. Okay, boundary conditions. Let's see if we can think of all 4 boundary conditions. Actually, writing down the boundary conditions is the last physical step of the problem solving, because as soon as we have all 4 boundary conditions, it's simple mathematics. Okay, so as soon as you have your differential equation set up, and you have your boundary conditions set up, and you have enough boundary conditions, then the rest is just math. Solving differential equations, plugging them in, playing around, might take a while, but it's just math. Physics is passé. So if we can write down all 4 boundary conditions, we're good. I hope. Can we write them all down? What are the boundary conditions? So you already mentioned one of them.
Normalization.
That's a normalization plus 4 boundary conditions. So you mentioned that, right?
It should be 0 because it blows up to infinity.
Right. So psi at x goes to infinity must be smaller than infinity. Something like this, right? Must be finite.
Doesn't it need to be 0 specifically?
Put it to 0. You're right.
Why is it?
We want in order for the wave function to be normalizable, we need the wave function to go to 0 at infinity. If it goes to a constant, it could still be normalizable, I guess. Actually, no, it couldn't, because you go to infinity. So infinity times anything is infinite. So you need the wave function to go to 0 far, far away. So that's one boundary condition, which will go to C. What do we know about psi at x equals 0?
I didn't understand how we
Excuse me?
I didn't understand how we know that psi at infinity goes to 0.
We know it, you can think about it physically, right? So we said that because it's a bound state, the classical particle will be strictly inside the well. The quantum mechanical particle can go inside the wall, sort of tunnel inside into the wall, but the longer the wall is,
So it's only psi 2. No. 3.
well, yeah, psi of x, which is split into different regions, as it goes to infinity, so obviously that's only in this region, because it doesn't apply to these two regions, right? That's where it applies. But yeah, so I'm saying that the longer the potential is, the less, the smaller probability of finding the particle, because it has to do a longer tunneling. You showed in your homework, I think, that the longer the wall, the harder tunneling is, right? You made a graph of it, or at least you were supposed to do so. You found that the decay was 1 over psi, hyperbolic sine squared. So that's a condition. Second condition, psi of x equals 0 needs to equal 0, because it has to be continuous. And it's 0 before, so it has to be 0 after. The derivative at x equals 0 does not have to be continuous, because potential is infinite. So the derivative will not be continuous. We don't care about it, we don't need to analyze it. We have two more conditions at x equals L. There's one condition on the wave function at L, has to be continuous, and the derivative of the wave function at L also needs to be continuous. That's how easy it is. Okay, first things first, we already told us, condition 1 kills C. Condition 2 tells us that A plus B equals 0. So if we plug that back in, we get 0 when x is smaller than 0. If A equals minus B, we get a sign here. Right? E to the ikx minus e to the minus ikx. It's a sign. So we get A sine kx. This A is different than that A, but don't care about that. It's just a constant. You can swallow other constants as it goes along. And since c equals 0, we have d e to the minus qx. Okay, the problem has already been reduced to like almost half.
It's not a problem that A is complex. Doesn't change it.
Was it complex here?
Absolutely.
So now it's I times a complex number, which is also a complex number, which is a different complex number. These integration constants are always allowed to be constant. The wave function is allowed to be constant. Is allowed to be complex. Right? The absolute value squared will always be real. And that's all we care about physically speaking. Wave function is not a physical observable quantity, so it can be complex. Okay, let's find the eigenenergies first. We'll use conditions 3 and 4. So condition 3 tells us that this is continuous when x equals L, so we get A sine KL equals e to the minus QL. And the second condition is that the derivative must be continuous. So we get K cosine KL equals minus Q, jumping to D, I'm missing D. Minus Q D e to the minus QL. Right? That's condition 3 and 4. I'm missing an A as well. Oh my God. Let's divide. So if we divide 4 by 3, fourth condition by the third condition, then we get a cotangent of KL equals minus Q divided by K I think that's it. right? Yay. Let's plug in K and Q. So I've erased them already. So we know K and Q in terms of the energy, right? That's how we define them. So we plug them back in and we get the cotangent of root 2me over h bar L equals minus root v naught over e minus 1. So all of the 2m and h bars and so on cancelled in this term. Obviously it's dimensionless because the cotangent is also dimensionless, and so is this argument, obviously. And you see that this is a transcendental equation for E, right? We're looking for E, that's our unknown. And it's a transcendental equation, it's the cotangent of the root of E that behaves somehow like 1 over the root of, I don't know, it's some weird equation that I could never guess what it equals, which is why I have to solve it graphically. But technically this is a solution, right? This equation defines the eigenenergies. And I'm saying plural eigenenergies because there could be more than one place, more than one E that satisfies this equation. And that's why there's more than one energy. Okay, so before we solve the equation graphically, let's just make a change of variables. I want to switch to dimensionless variables. So it's easier to look at it that way. So I'll define theta, which is just the argument of the cotangent, and I'll define theta 0, which is the same thing, but with V0 instead of E. Using this change of variables, the equation becomes cotangent of theta equals root of theta 0 over theta squared minus 1. Now the condition that the energy must be between 0 and V0 just becomes the fact that theta must be between 0 and theta 0. That's obvious. This also makes sense because you look at the right hand side here.
Where's the minus?
What minus?
The equation.
Yeah,
The original
minus
equation.
Add a minus. Still have a minus. You're right, there's a minus here. What am I saying? So this condition also makes sense. If you look at the square root, if you plug in theta larger than theta 0, then this becomes imaginary. Because if theta is larger than theta 0, then this is smaller than 1. Right? Something smaller than 1 squared is even smaller. Minus 1. Right? That's negative number, take the square root, it's imaginary. And obviously a real number will never equal an imaginary number, so there's no solution for theta larger than theta 0. That just reflects the condition that E must be smaller than V0. That's cool.
So it's conform our condition.
Excuse me? It confirms our condition. Yeah. It's always nice to see. In the perfect world, mathematics and physics are exactly the same. In the real world, they're not. But that's what we wish for. Okay. So we have our transcendental equation in terms of theta, but you realize theta is just some function of e, so if we know theta, we can find e just by multiplying by a couple of constants. So let's do the graphical solution. There are 3 steps to it. First step, plot the left-hand side. The function of theta. Second step, plot the right-hand side for different values of theta 0. And I recommend that you play around with it a little bit. When using a computer, just plug in 10, plug in 100, plug in 1,000, plug in 1, plug in a lot of different numbers. And see how it behaves. You might learn something about the physics. And then the third step is simply that the points of intersection, they are the solutions. So you just read them off. I can read off the value of theta, I can then find the energy, which is what I'm looking for. That's how simple it is. Right, so let's do so. This is theta, this axis. This is pi, 2 pi. This is pi over 2. This is 3 pi over 2. So a cotangent comes from infinity, crosses 0 at pi over 2, and then goes to minus infinity at pi, right? It's a cosine divided by a sine. And then it's periodic, so the same thing again. And again and again and again. Okay? That's the cotangent. Now we can plot the right-hand side. So that's this weird-looking function. See, it's negative, so it'll always be below the theta axis. It's a negative number always. So it looks something like this. This is for some theta 0, and if you make theta 0 larger, it just goes over here. So in the red case, theta 0 is larger. In the purple case, we'll try to indicate that. So this is larger than that.
Don't it reach 0 somewhere?
It's going to reach 0 at theta 0. When theta equals theta 0, let's indicate that as well. Depends how you choose your theta 0. So let's indicate that. You see it right away, right? When theta equals theta 0, it equals zero. You see it right away. You plug in theta equals theta 0, you get 1 minus 1. So right-hand sign vanishes for theta equals theta 0, and we already said that beyond that it cannot exist. It's imaginary. So let's focus, for example, on the purple case. We have 2 points of intersection. So there are 2 eigenenergies. Read off the values of theta here and here. I have colors to use. just like scanning on a computer, take like, say, two numbers out of a decimal point, whatever accuracy you're looking for. Don't go overboard, just like indicate that you realize what you're doing. Plug it into here, eliminate E, you find your eigenenergies.
How did you know where to put the theta zero?
What do you mean?
You can put it further away, and
So I said, in this step you play around with theta zero.
so I can have an infinite amount of solutions.
No, given theta zero is defined by V0. Right, so in any question you're given V0, then theta zero is a constant, but because it's a parameter for us, right, so play around with it, you'll find different things. For instance here, you see that as theta zero grows, you'll get more and more solutions. Right, in this case, in the purple case, there are two eigenfunctions, two eigenenergies. The next cotangent will start at 2 pi, and let's say if here is 5 pi over 2, right, so it'll look like this. So there'll be another solution in the red case. So in the red case, where theta zero is larger, you get 3 eigenenergies. There are 3 possible bound states. And in the purple case, there are 2 possible bound states. That's why it's nice to play around with theta zero. You'll learn that the deeper the well is, the larger V0, the deeper the well is, the more bound states you get. Which makes sense, obviously, physically speaking, and you see it reflected in your analysis. Questions about this? Okay, so we found our eigenenergies. Yay! Let's go ahead and solve the second part of the question. We were asked for the minimal depth. So we were asked what is the minimal V0, so the minimal depth of the well, such that at least one bound state exists. Any ideas how to solve this? So we already talked about it, how when theta zero becomes larger, I get more and more bound states. So obviously when theta zero becomes smaller, I get less and less bound states. So if theta zero is somewhere here, say here, there still is one bound state, right? It's going to be like this, there's one bound state. And when theta zero is over here, there's no bound state. Because the left-hand side and the right-hand side never intersect. So no energy satisfies the transcendental equation. Where does this transition happen? As theta zero equals 2 pi over 2. So the condition is that theta zero is larger than pi over 2. Everyone sees that? That's what's good about drawing graphics. You can afterwards analyze them graphically. And that's why I say play around with this theta zero, because you'll discover it automatically. Just play around enough. Use some physical intuition, right? Larger is more, less is less, you'll get there. So we plug this back into the definition of theta zero. We find that the minimal V0 V0 must be larger than this value for a bound state to exist. So if V0 is smaller than this value, the potential is too shallow for a bound state to exist. It's not deep enough. That's pretty cool. Okay. One more step. We were asked to find the Eigen Functions. So we were at the stage where we had this, right? And then there was a d, I think, e to the minus qx, right? This is what we had. And we then used two initial conditions and divided by them to eliminate both A and D from the equation, and look at the equation for the energies. But now the energies are known. Hence, K and Q are known. So we can treat K and Q as numbers that we know their values. If we know E, then we know both K and Q. So there are two there are two unknowns. So we'll first use, let's say, boundary condition 3. It doesn't matter, you can also use boundary condition 4. But I'm going to use boundary condition 3, which is the continuity of the wave function itself. So that's A sine KL equals d e to the minus QL. From here we get that d equals A sine KL times e to the plus QL. Plug that back into there, you get psi of x equals 0, A sine kx, and A sine KL e to the minus q x minus L. So I used one of the boundary conditions, not both of them. We saw them. If I use both of them, I'll eliminate both A and D and then remain with the energies an unknown. So I'll use just one of the boundary conditions, eliminate one of the integration constants, and now I can use the normalization in order to find A. So 1 equals integral from minus infinity to plus infinity, psi x squared dx. Now watch out, this is an important step. Don't get confused. I am not normalizing A sine kx and then normalizing this. No. I have to normalize psi. So the integral from minus infinity to plus infinity over the entire psi x, so this and this and this, needs to equal 1. What I'm saying is that there's the integral from minus infinity to infinity to 0 over 0 dx. That's this part. Then there's the integral over sine squared kx dx from 0 to L. And then there's one more integral from L to infinity over e to the minus q x minus L dx squared. There's 2 here. Very important. This is obviously 0. Very important, I'm normalizing psi. It's the wave function that is normalized, not the individual parts. It's obvious, but I've seen a lot of people make this mistake. Then you get a different A than here, and you start getting worried that something's going wrong. And you're right, something is going wrong. You're doing something wrong. You normalize properly, the entire wave function is what is normalized. Okay, you solve this integral. I'm going to skip the actual solution. You solve the integral, eliminate A, you find that A equals some really big and not nice expression. I will leave it as a function of k and q, because as I said, k and q are known. Plugging them in will just make this entire thing even uglier. So it's 1 over the root of this thing. So yeah, as I said, it's not very nice. That's just a fact of life. Plug this back into here, and you're done. So if you plug A back into psi of x, done. That's a solution. Okay? Questions? This is how you solve finite potential well problems. Any potential function that you might encounter during your homework this week. And I promise you there are a couple of them. This is how you proceed. This is how you go at it, solve the question. Okay. So if there are no questions, we'll proceed to our second example for this tutorial. We're going to solve an infinite square well with a delta barrier inside. What does that mean? We're considering the potential that equals beta times delta of x. Well, x is smaller than some L in absolute value, and it is infinite outside this area. So if this is x and this is v of x, then the potential is minus L, this is plus L. It's infinite out here, infinite here, and there's a delta function at x equals 0. So exactly in the middle, there's this delta function. Notice that the length of the well is 2L, not L. This is just a personal preference. I don't want to go writing L over 2 all the time. So it's going to find plus and minus L as the boundaries of the well. My well is then of length 2L. Okay, we want to find the bound states. Of course, there are only bound states in this problem because it's infinite on the sides. Both the energies and the wave functions, or just the energies? I don't remember. Not quite sure if I find all the. I think just the energies. Let's see how far we get. And then we would like to discuss the limit of beta goes to 0 and the limit of beta goes to infinity. So the limit in which the delta function vanishes, which is returned to a regular infinite potential well. That should also happen with the energies. And then in case of beta goes to infinity, try to think what happens in that case. If you have an intuitive answer to that as well. Okay, so the Schrodinger equation, obviously we have to split up space. On the there's a space, the region on the left of the delta, and the region on the right of the delta. You already know that there's some weird stuff happening where the delta is. We saw it last time already. But the Schrodinger equation, of course, looks the same on both sides. It's just minus h plus squared over 2m. Second spatial derivative psi of x equals e psi of x. Of course, E can take any value between 0 and infinity. And so the solutions on those sides there's the area where x is between minus L and 0, and there's the area which is between 0 and L, the left and the right, between 1 and 2. And we'll use cosine and sine this time. We could use exponentials, we could use cosine and sine. It turns out that in this case, it is easier to use cosine and sine. I'll tell you the reason why you would think that. But of course, you can also use exponential functions with e to the ikx and e to the minus ikx, and you'll get the same place. Well, it just might take you a little longer. Where k, of course, as usual, is root 2me over h bar. Okay, that was the easy part. Now I want to implement a theorem that you learned in class. You learned in class in the lecture theorem that has to do with parity. You learned that if a potential is symmetric, so v of x equals v of minus x, which is the case here, then the eigenfunctions have a definite parity, which means that they are either even or odd. This is a theorem we proved in class using the parity operator, if I'm not mistaken. And we're going to implement it. I'm not going to prove it. We've done it already. We're now going to use this to save a lot of work. This theorem saves a lot of work in solving problems of this kind. Now, what the theorem means is that an eigenfunction does not mean that all our eigenfunctions are either even or odd. It means that there are even eigenfunctions and there are odd eigenfunctions. One eigenfunction is either odd or even, not something else. It has to have a definite parity. But you can find both even functions and odd eigenfunctions, which means that we can just deal with both cases individually. We will first deal with the even kind, even wave functions, finish them off, and then separately deal with the odd wave functions. So the even wave functions, they satisfy that psi of x equals psi of minus x, which means that if I take, say, this part, right, exchanging this part x for minus x, it must be equal to the top row. Anyone sees that? So if we switch x to minus x in psi of, right in the bottom row, where x is positive, must be equal to sine the negative part. Or if we're going to use a formula, we get sine of cosine kx. Cosine of plus x and cosine of minus x are the same. It's an even function. Minus d of sine kx, because sine of minus x is minus sine. And that must be equal to the top row. So that's a cosine kx plus b sine kx. And we automatically learn that A is equal to C and B is equal to minus D. Because cosine and sine are orthogonal. So we just compare their coefficients. So the even wave function, if we plug this back in,
Sorry, you think that's why you have a minus in the D?
I'll give you in a second.
Minus C.
I switched x from minus x in the bottom row. So cosine of minus x is cosine, but sine of minus x is minus sine. I'm forcing the wave function to be even. Right, I'm dealing with even wave function, so I have to build an even wave function. And this is how I force the wave function to be even. Okay. So where are we? Okay, what do we do next? Boundary conditions. You see, it's simple, it's always the same. So first boundary condition, continuity, right? Guess what? That's automatically satisfied, right? Plug in x equals 0, the sign goes away, cosine equals 1, you get a equals a. So it's already truly satisfied. And even need to use a boundary condition because it's an even function. How cool is that? Where am I? Okay, there's one more. Okay. Next boundary condition. Psi at x equals plus minus L is equal 0. Right? Because inside of the infinite wall, psi is 0. Has to be continuous at the borders. So we plug in x equals L, we need to find, we can express A in terms of B. Let's just do it for one of the sides. So let's just do it here. For instance, we get, for positive L, so at x equals L, we get A cosine KL minus B sine KL. That equals 0. So we find that B equals to A times the cotangent of KL. And then we plug it back in. So we get psi even of x. A times the cosine kx plus A times the cotangent KL sine kx. And it's getting longer and longer, eh? The only difference between the two is the minus sign. Obviously, we could now find A by normalizing, which is not what we're going to do. Yay. But of course, that could be done. It's just some unpleasant mathematics, but it can definitely be done. Just note that you can find A by normalizing. What we're interested in are the energies. So for that we need one more equation. And that equation is the discontinuity of the derivative. So let's just prove the discontinuity again. Let's see what it is in this case. So we start from the Schrodinger equation, including the potential. And we then integrate on both sides from minus epsilon to plus epsilon and take the limit where epsilon goes to 0. We did this last time already, so I'm doing it quickly this time. Also, I think we're running out of time. Kind of. So we take limit. Epsilon goes to 0. So here we get the first derivative. Right? The integral of the second derivative is the first derivative. So we get psi prime at epsilon minus psi prime at minus epsilon. The integral over the delta function just picks out the value of psi at x equals 0. And on the right-hand side we get 0 because the integral of a continuous function is continuous and we're evaluating it at the same point in the limit epsilon goes to 0. So it's always a 0. So we use this condition. Let's plug in our psi. Take here our psi. We take the derivative and plug in x equals 0. So the derivative of a cosine is a sine, which vanishes at x equals 0, and the derivative of a sine is minus cosine. And then when we plug in x equals 0, will give us 1. So we just take out the minus sign. So when I plug in the even wave function, I'll get h bar squared over 2m minus ka cotangent kl minus ka cotangent kl equals beta times a. A is just the wave function at 0. Look at the wave function at 0, then the sine disappears, cosine is 1, result of a. Play around with this, we find cotangent of KL equals minus m beta divided by h bar squared k. And then, something is right. Yeah, the 2 over the 2 multiplied by m, divided by h bar, divided by a, yeah, I'm fine. Or we could just flip this around, which might be easier to look at. If you prefer a tangent, just do 1 divided by this thing. With h bar squared k divided by m beta. Obviously, this is a transcendental equation for KL. So let's just multiply by L and divide by L, okay? Because we want the argument here to appear here as well. So we just multiply and divide by L, and it is then a transcendental equation for KL. We treat KL as a variable, set KL equals theta if you must, and then analyze, right, draw this function, which is quite easy. It's just a negative decline and a tangent, and you can find the eigenenergies by solving it graphically. Let's say we found the points of intersection. Let's call them Zn. We can make a list Solve this graphically. So a tangent is this thing, and this is minus KL. I think it'll go through 0, right? So we find the intersection points, read off the values, and we can now make a list. Let's call this Z1, Z2. You see there's an infinite amount of them. It'll always continue, which reflects the fact that the potential is infinite. So we can make a list of all Zn's. So we can say Z1 equals whatever, Z2 equals whatever. That is the KL axis. So get solutions for Zn equals, the other way around, when KL equals Zn, K is the energy, right? It's the root square of the energy. So if you know K times L, you know the energy. It's just a bunch of constants between the two. And if you have Zn, you can then write the even energy, the energies of the even eigenfunctions. They're h bar squared Zn squared divided by 2ml squared. In case of where there's no delta function, Zn will just be n pi. But in this case, because there is delta function, the Zn are not regular. They won't be equally spaced, or they won't be spaced by an integer number. They won't go like n squared, as in the regular case without the delta function. There will be some weird numbers which you obtain graphically and found numerically by zooming in. So these are the eigenfunctions, the eigenenergies, of the even wave functions, the even eigenfunctions. Okay, let's analyze the odd case. So for the odd wave function, we now want the opposite to be true. This time when we switch x to minus x, I'm not erasing because I need it. When I switch x to minus x in psi on the right hand side, I need to get minus psi on the right hand side. Sorry, I'm replacing on the right, so on the left. Right, that's the definition of an odd function. So I get c cosine kx minus d sine kx must be equal to minus a cosine kx minus b sine kx. From here I automatically get that e equals minus c and b equals d, and hence the odd wave function, oh, this is great, I'm right on time. Cool. I'm sorry for doing this, but the only difference is that there's a minus sign here instead of here. I usually don't do this, just I'm going to release you more or less on time. So we get the wave function in the odd case. Next, we use boundary conditions. So from the continuity of the wave function, we see that a plus b, is equal. So the signs go away. We found a equals minus a, right? That implies that a equals 0. Which number is equal to its negative? I know only one such number, it's 0. So this whole part vanishes. It's not a big surprise that in odd functions there's a sign. Probably could have guessed that.
Although in the previous case we had...
Yeah, I'm thinking about the same thing right now as well. It's interesting, right? We had a cosine, it was cosine plus sign and cosine minus sign. And plus sign and minus sign is even, right? Plus sign on one side and minus sign on the other side is an even function. It makes sense. So you think about it. And don't catch me off guard. So we find a equals 0, the cosine vanishes. It worked in the other case because sine is 0 at x equals 0. And that way it's still continuous. In this case it wouldn't work because of continuity, I think, because cosine equals 1. Right, that's why it had to disappear. So this is, where are we? Okay, and now we think about the derivative. Okay? Now notice that the derivative of the wave function is automatically already continuous. I mean, it's the same thing. It's just psi out of x is just b sine kx everywhere, right? It's the same on the left and on the right. So this function the derivative is continuous, although it's a delta function. Why is that so? Because it's 0. Because the wave function vanishes where the delta function is. So it doesn't even feel the delta function. Because the probability of finding the particle where the delta function is 0. So it doesn't feel a delta function. Derivative is continuous. Psi odd x equals 0 equals 0. So it does not feel the delta potential. Okay, that's good to know. Now we can use the last condition. The last condition tells us that the wave function must vanish at plus and minus L. Right, and closed boundary conditions, because it's an infinite well. Excuse me?
Wasn't the derived thing not continuous?
What was not continuous?
The derivative.
So it is continuous, and there's nothing you can do about it. And you can, the reason for it is, right, because, where's our condition? Just raised it right now, didn't I? The condition was up to some constant at psi prime of plus epsilon minus psi prime at minus epsilon was equal to psi 0. But psi at 0 is 0. So the derivative is continuous, also by the formula. I was trying to give you physical intuition, but of course mathematics agree with what I'm telling you. Almost managed. But not this time.
So we get eventually that the delta function does not affect
the odd wave functions.
The odd functions at all. Even the energies will stay exactly like the infinite potential.
Very good. Very good. Using the last boundary condition, namely that psi of x equals L must equal 0. At x equals 0, it's automatically 0 because it's the sign. So at x equals L, we get the condition that KL equals n pi, and hence the energies are exactly the same as the energies of a regular infinite potential well. Notice the length is 2L. So there's going to be a 2L squared. If you follow the mathematics, you'll get it automatically. Sorry, you don't get that. You get the regular L. You get the regular L squared. But it will make sense. I promise it will make sense, and I'll prove it to you.
And define, you put 2n and 2n instead of n, 2n. This is what he did in the paper.
Excuse me?
This is what he did in the papers. Instead of n, you wrote 2n, and instead of n, you wrote 2l. Then you
And then use the 2 upstairs as well.
yes.
That's what I have to do.
Then you can see that it's like an
Right. That's exactly what you in the papers you wrote. Ah, yeah, you're on my papers. Read on. Okay, so let's interpret what we found.
Can you explain again why is it?
I'm going to explain right now. It's the last half a page, which I have 3 minutes for. So let's interpretation of odd energies. Let's interpret them. So what you see is you can rewrite it by simply multiplying by 4 or by 2 squared, the bottom, top and the bottom. And now you see this is the odd. So don't get mixed up between even and odd. There's a problem here because even and odd applies both to numbers. 2, 4, 6, 8 are even numbers. 1, 3, 5 are odd numbers. It also applies to functions, but it's a different meaning. An even function and even number are 2 different things. So the Eigen Functions with odd parity are equivalent to the even-numbered energies of an infinite potential well. Okay, so it's the odd parity, but even-numbered. 2n is an even number. So if you look at this as a wave, so this is just, as you were saying, because the wave function vanishes where a delta function is, you can simply totally just forget about a delta function, and you're left with a potential well of length 2L. Because the wave function, the odd parity wave function vanishes where the delta function is. You just forget about the wave function, forget about the delta, forget about the potential, and you're left with the regular infinite potential well. Now what happens in the even parity case? Let's interpret the even case. So we saw that the eigenvalues are altered by the delta function. The fact that there's a delta function sort of shifts the energy levels away from the value of the regular infinite potential well. But we can still get some nice physical intuition by taking different limits. So let's first of all look at the case where the delta vanishes. Vanishing delta. So that's the limit where beta goes to 0. In this case, we expect to obtain the missing energies for the regular potential well, right? So let's look at our function, our transcendental equation. where tangent of KL equals minus h bar squared over ml beta KL. And I'm taking the limit where beta goes to 0. So if beta goes to 0, this goes to infinity, right?
By half.
So the tangent of KL is equal to infinity if KL equals n pi. Sorry? It's a cosine upstairs. 2n plus 1 pi over 2. So it's at pi over 2 it diverges, and then at 3 pi over 2, so on. Every full goes to minus infinity, to be exact. And if we plug this back in, we find that the even energies are the missing ones. Again, the length is 2L, and this is an odd number. So the even parity wave functions, or Eigen Functions, correspond to the odd numbered energy levels. One more thing I'd like to tell you about is what happens when beta goes to infinity. But you see, as the wave function, as the delta vanishes, it's exactly the same as solving the regular infinipotential well, and we get both solutions, both the even and the odd wave functions. And you've solved the symmetric well in your homework, so you should be familiar with the solutions and with the energies, with the fact that there's an even and an odd case. So, last step, let's take the limit where beta goes to infinity. This is good for our physical intuition. When beta goes to infinity, the right-hand side here goes to 0. So when is tangent equal to 0? When the sine is equal to 0. This is KL equals n pi.
We have two wells. It means we have.
Very good. So we get KL equals to n pi, which is the same condition that we found for the odd wave functions. Right? So this is like having two wells. In this case, we get so now this was minus L, this was plus L, and then the delta in the middle now went to infinity. So now we automatically have two wells because we need the wave function to be even. So there's a ground state here, another ground state here, and then there's a first steady state here, and a first steady state here. So the well is effectively split into two wells. Second. Of length L, which is half of 2L, right? Half what we had beforehand.
In the even energy, you don't need to make n into 2n because it's only even. This n came from this condition. There's no condition on n being even or odd, right? We got this condition. We're taking the limit beta goes to infinity, so tangent needs to equal to 0, which means that the sine is equal to 0, which means KL needs to be equal to n pi. We then plug it into the definition of K, and we automatically obtain this. It means that, right, this is L, this has to be L, it's just one side, right? That's why I say it splits to two. Basically, if the particle starts off here, it will never get here. And if it starts off here, it will never get here, because there's an infinite potential well in the middle. Infinite barrier in the middle. Even though it's infinitely small, it's still infinitely high. We saw in last lecture that such a delta barrier is impenetratable, even though it's very thin. So
basically just splits space into two halves. You start on one side, you kind of go to the other side. It's a singular point of space. Questions? Cool. So enjoy your homework, and I'll see you next week.